When we're simply counting and manipulating whole objects, integers are fantastic. But sometimes we need to deal with numbers in their more mathematical sense, and we need a data type that will allow us to express ideas that are not entirely whole numbers. Floating point numbers, or floats, are a Java primitive type that allow us to express numbers that have decimal points and fractions. In this video, we'll be modifying some float and integer variables side by side to see how they are similar and different. So let's start by declaring two variables, one an integer and one a float. As we know, once we've declared these variables, we're free to modify and assign to them in future lines of our Java program. Let me quickly show you that we can also modify and assign to these variables in the same line that they're declared. So on line 7, where I have declared my iNumber integer variable, I'm free to immediately give it the value of 5. You'll notice that if I try and do something very similar with our float variable, NetBeans is going to yell at us. And in fact, if we attempt to compile our program, we're going to get a legitimate compiler error message. When we use an explicit number in Java, that is, typing out the digits rather than working with a variable, that value still has to be given a type in Java. When we type out a number without any decimal places, the type that it's assumed to be is integer. So our assignment on line 7 works just great. However, a number with decimal places is assumed to be this type called double, which we'll talk about a little later. It's a sister type of float, but it's not quite the same. So what we need to do is tell Java to treat this 5.5 here as a float type number. To do that, all we need to do is put an F after the digits. Okay, to make sure we've gotten that syntax all right, let's give our program some super basic functionality. Let's use system.out.println to print in sequence our integer number and then our floating point number variable. When we build this program, our compiler error has gone the way, and when we run it, we see the two assigned values as expected. Nothing too exciting there. Now, rather than assigning explicit values to our variables, let's do some basic arithmetic so we can see how integer and floats, when modified in Java, behave differently. In Java, both floats and ints are primitive types, the logical building blocks of the programming language. That means that we can compare and modify them using mathematical operators like division. We know that if we attempt to divide one integer by another, we'll always get a whole number as a result, even if the rules of standard mathematics don't make that the expected result. If we divide a floating point number by another floating point number, however, we'll get a more mathematically accurate result. Sometimes Java will let us do things that might not be such a good idea. For example, instead of attempting to set the value of our floating point variable to one floating point number divided by another, we can instruct Java to set its value to one integer divided by another. Because the computation on the right side of our equal sign occurs before we change the value of our floating point variable, we're going to see the same phenomenon in this 5 divided by 4 as we see when we divide 5 by 4 above, because both of these 5s and both of these 4s are integer variables. So when we run our program here, even though f number remains a floating point number, as we can tell because it prints out with the decimal place, its value is still set to the rounded down whole number of 5 divided by 4. Solving this problem is pretty straightforward. We simply need to change one of our integer values to be a floating point number. And now the computation will know to proceed with decimal place division. This becomes a little trickier and more important to navigate properly when we stop working with explicitly declared numbers and begin working with variables. Let's declare two integer variables now. I'll just call them I number 1 and I number 2. And rather than attempting to set the value of f number to one explicitly declared number divided by another, we'll set its value to integer variable 1 divided by integer variable 2. And we'll just print out the result stored in f number. When we run this program, because once again we're dividing one integer by another, we're going to see the rounding down phenomenon. The value being stored in our floating point variable is 0.0, the rounded down result of 5 divided by 6. If we were working with explicitly declared numbers, we would solve this problem by changing one of these two numbers to be treated as a floating point number, simply by putting a decimal place and an f after it. In this context, that's not an option, because rather than thinking that we're asking it to treat I number 2 as a floating point number, Java now believes it's looking for a variable called I number 2f, which certainly doesn't exist within this context. We can achieve a similar result, though, by using what's called a cast. This is a command in which we ask Java to treat a variable of one type like it is another one. Here we're circumventing Java's natural inclination to treat I number 1 and I number 2 as integers. We're stepping in and saying, you know what, Java, treat this number here as a float. And we're assuming some responsibility when we do that. Java is going to attempt to do what we ask. But if we've chosen poorly and attempted to cast one object to an object that it cannot be, our program will crash. Fortunately, we're working with primitives here, and the primitive types know how to act like another type. So we can cast the variable I number 1 to temporarily operate like a floating point number by prefacing it with parentheses float. Now if we run our program, we'll see the expected result of 5 divided by 6. And that's a pretty solid introduction to working with floating point numbers, which we're going to use just about any time that we want to be working with numbers in their mathematical sense, rather than as integers for counting whole objects. In the last couple of minutes of this video, if you're feeling up to it, let's quickly talk about the double. The double is a sister type to the float. It provides a greater resolution. Double numbers can have even more decimal places, basically, but they take up a little more memory. At this point in time, using doubles or floats is almost always a style or personal preference decision, as unless you're working with complicated software that must run at peak memory efficiency, the extra memory space taken up by a double is not very significant. Let's see. To illustrate how doubles work, let's change our two integer numbers to be doubles. Right there, I've just changed the names of the variables, so the logic of our program hasn't changed at all. But here, when we change the declaration of these variables from declaring integers to doubles, now the logic does change. Anyway, when we explicitly declare a number with decimal places, it defaults to being a double. And now we need to fix line number 9. Line number 9 is an issue because dividing by a double is going to return us a double result. We can solve this issue in two ways. First, we could cast d number 1 and d number 2 to floating point numbers and then divide them. However, dividing our two double numbers by each other is a perfectly legitimate operation. So why not allow that to occur as it would naturally, and then cast the resulting double to a floating point number, preserving a greater amount of our resolution. Just like in algebra, we can break up conceptual blocks of our program that we would like to occur before another block using parentheses. Now, if we run this program, we get an expected result. Thanks for watching.